So the next application of adversarial learning that we are interested in looking at is what is called as adversarial learning for domain shift. For handling domain shift. So this idea of adversarial learning that we just saw, which is using a min-max optimization problem for translating one distribution to the other, is not restrictive only for only to generative models. It can also be used in a gamut of other applications. I'll show you one sample application where adversarial learning can be used beyond generative tasks. So that the task that we are interested in as an application of adversarial learning is what is called as the problem of domain shift. Now, what is the issue of domain shift? Let us look at that. Suppose we have data from a distribution let's call this ds, okay, which is tuples of sorts of x1 comma y1, x2 comma y2, and we have xn comma yn. So this data has been sampled IID from a distribution ps. So this ds, okay, is called the source distribution. Now the task is to come up with a classifier for source distribution. Okay, let's say that the task that we are solving is that of classification. So we know that all classifiers would estimate the conditional distribution of y given x, right? This is what every classification task would solve. So we are interested in solving a classification task. However, what happens is, in practice, the distribution that we would want to test out our classifier on will not be same as that of the source distribution. So what happens is, during test time, data comes from a different distribution. Comes from a distribution that is different from ds. Okay, so which means that there exists another distribution, okay, call that dt, okay, which is the target distribution. Let us write it here itself. So during test time, the data comes from a distribution dt which is different from ds. So mathematically, ds or dt that comes during the test time is not the same as the source distribution. In those scenarios, what happens is, the classifiers or any kind of regressors, it doesn't matter, some function approximator that we have trained on our source data, okay, classifiers or regressors trained on ds would fail on dt. It's obvious, right? Suppose you have a data on which you have trained a classifier. Whenever it comes from, and when the test data comes from a different distribution than the data upon which the classifier has been trained, then the classifier is bound to fail. So let me show you an example of what I am talking about here. So this is, so there is a standard data set for this. This is called the PAX data set. Yeah, here is an example of what is called as the PAX data set. So there we have data coming from 4 different distributions. One is called the photo, the other is called art, painting, the third is cartoon, and the fourth is sketch. Let's say that our training data is coming from one of these 4 distributions, okay, and you have trained a classifier on this. But as human beings, we have no problems in identifying what the class category is, irrespective of the distribution that it comes from. However, if a neural network is trained to classify the data from, let's say, photo distribution, and during test time if I start showing it data from sketch distribution, then the classifier that has been trained on the photo distribution fails. Okay, so now the question that is of interest in domain shift or domain adaptation is, can we come up with a method where classifiers that have been trained on source data would continue to do well on a target distribution that is similar to the source distribution but not exactly the same as that of the source distribution. Okay, so now let's call this the problem of, it's called unsupervised domain adaptation. Unsupervised domain adaptation. UDA. So here the problem setup is the following, that we are given the source data, which is same as the one that we just described. We have xi comma yi that have been sampled from a source distribution, and we are also given the samples from the target distribution. Let's call them as x cap I. So I is 1 to m, or let's call this as xj cap. J is 1 to m. This is sampled IID from a target distribution pt. Okay. Now please note that the problem setting in unsupervised domain adaptation is that we have access to source data, where we have the source images or source data from the source distribution and the corresponding labels. But from the target data, we only have access to the raw data without the labels. Right? So this is the setup for unsupervised domain adaptation. There are cases where this assumption that we have access to target data without labels is also relaxed. Those kinds of problems are called domain generalization problems. It's not the focus of this particular course. I'm just showing you where the idea of adversarial learning can be used. So the problem of unsupervised domain adaptation is where we assume that we have, during training time, we have access to the data from the source distribution along with its labels. We also have access to the data from the target distribution, but we don't have access to the target labels. Sometimes this is a practical assumption to make, because it is not very difficult to get data. What is difficult to get are the labels. So let's say that we have data from the source distribution along with the labels, and from the target distribution we have only the data without the labels. Okay, so we have PT, or the source distribution, is not the same as that of the target distribution, right? I mean that this is what is called as the domain shift. There is a domain shift. Okay, the question is, the objective of domain adaptation is, given ds and dt, learn representations or features or classifiers such that it performs well on both the source data and the target distribution PT, right? The question is, can we learn a classifier or a feature representation, okay, such that the classifier or the feature representation that we have learned will perform well both on the source data and the target data. Now, suppose we build a classifier only on the source data, it will not perform well on the target data. Now that we are given some examples from the target distribution as well, can we learn representations in such a way that it performs well on both the source data and the target data? So this is the task that we have. Turns out that this task can be solved using adversarial learning. Okay, I'll just show you that. So it can be solved using adversarial learning using this method called domain adversarial networks. Domain adversarial networks, DANs. So we can use domain adversarial networks to solve the problem of domain adaptation. How do we do that? So here we have a neural network that is used as a feature extractor. So we have a neural network. Let's call this as phi of x. Okay, this will take both x and x cap from the source and the target distribution as inputs. Okay, so this phi network maps from data space to some feature space. Let's call the feature space as some thinking what alphabet to use, some f for feature space. So this will give you a feature vector. Let's call this f of s and f of t. Okay, now what is f of so the feature vector that we get on the samples from the source distribution, I am calling them as fs, and the feature vectors that we are getting from the target distribution, I am calling it as ft. So this will, so whenever x goes, it will give you fs. Whenever x cap goes, this will give ft. Okay. Now we have another discriminator here. And this discriminator would discriminate between, let us call this as TW of f, and this discriminator would take fs and ft as input. Okay, and this would, as usual, give you values between 0 and 1. Here, let's say that fs, the features for the source distribution, has a distribution pfs, and the features from the target distribution has a distribution pft. Okay, now if you think about it, this entire structure that we have here is a GAN. So we train this adversarially, that would match PFS with PFT, right? So if you recall what a naive GAN does, naive GAN would take distributions from the naive GAN is trying to make distribution of P theta to be same as that of Px, right? Here we have two distributions, PFS and PFT, And this entire setup can be trained adversarially to ensure that the distributions of PFS and PFT are the same with each other. Right? How do we do that? We'll train. So let us write that down. There is this phi network which will be acting like a generator, and there is a discriminator network. So we want to solve the same min-max adversarial problem. Now, what is the loss function that is used here? We have the expectation of log of, okay, let us call this dw, because we have been using d for discriminator, dw. This is log of dw, and this will take samples from fs, right? So this is over pfs, plus we have expectation of log of 1 minus dw. The data is now coming from ft. This is PFT. So we know that we can use adversarial learning to match distributions, right? I mean, ultimately adversarial learning is a technique that is used to match distributions. Here what we are doing is we are trying to learn these features phi in such a way that the distributions of the feature vectors that we are getting for the source distribution and the target distribution are exactly the same. Okay. Now this would ensure that irrespective of the fact that the data is coming from the source distribution or the target distribution, this phi network is going to give you features that comes from the same distribution. So this phi network in a way is trying to learn features in a domain adversarial fashion. Okay, it does not care what the distribution the data is coming from. It will ensure that the features have been learned in a manner that is agnostic to the domain. But there is also an issue here. The issue is that while the feature distributions are made the same, there is no guarantee that the features that we are learning here have to be conducive for the final classification task that is at our hand. Okay. To ensure that, what is to be done is that we should learn another classifier simultaneously. This is the GAN. So we have another classifier here. So this classifier only takes features from the source distribution. So let's call this H psi, that will take fs and gives you labels from the source distribution. So this is coming from, so py, what did we call it, psy given x. Yeah, this is estimating the posterior of the source labels. Yeah, this is source labels given the source data. This is simply a classifier for the source distribution. So we have a classifier for the source distribution. Now what happens is that the phi network is trained with two objectives. One, we need to train the phi network to ensure that the distributions of the features are the same irrespective of it's coming from source or data. We also have to train the psi network, which is the classifier network, to minimize the cross entropy loss. So binary cross entropy loss between y, which is the source data, and the output of this features coming from the source distribution. So the classifier has to be trained in such a way but we also want our phi network, okay, to be trained to ensure that the binary cross entropy, which is the classification loss, is also minimized. So what happens is that this phi network has gradients flowing from two different directions. We have gradients flowing from the classifier's output. Write that down. So phi has two objectives. One is the adversarial objective, right? So the other is the classification objective. The adversarial objective would ensure that this phi network has been trained in such a way that the features that we are getting are agnostic to the domain. The classification objective would ensure that the features that we are getting are conducive for the classification task, because otherwise, if you only train the phi network in an adversarial way, sure, it will learn to find the features that are agnostic to the domain, but those features may not help the classification task. Okay. Now, since we also have the labels from the source distribution, we will use them in this classifier, and we train this phi network simultaneously, not only to ensure that it will give you features that are domain agnostic, but also that it will give you features in such a way that the final classifier is also trained properly. So now when we train these networks simultaneously, that is, we train our feature extractor to ensure that the features are domain agnostic and the classifier also classifies well on the source data, then the hope is that this classifier, okay, is learning to classify using features that have been learned in a domain agnostic manner, which means that post training, okay, during inference, the same classifier which is H psi star can be used on both the source and the target data. And target distributions. So why is this? This is because the classifier has been trained using features that are agnostic to the source. So now we have ensured by adversarial training that the distribution of the source features matches with that of the target features, which means that a classifier that is trained on the source features is same as a classifier that would have been trained on the target features. However, now since the classifier, we only have labels for the source features, we will train the classifiers with the source feature. During inference, the same classifier can be used both on the source and target data, as long as the features are used as input. Used in the input. So what does that mean? Given a data point x cap that we have sampled, so let's call this as x cap test. So we have a data point x cap test that is sampled from p test. Okay, then what we should do is that we should first find out f t test, the feature vector corresponding to this, by passing that through the trained feature extractor. We pass x cap test through the trained feature extractor. Okay, we get f, the feature for this particular test data set. Then the final output, or the class, which is y cap test, is simply the output of the classifier, which would take ft test as input. Now note that since phi would ensure that the distribution of the source features is same as that as the target features via the adversarial training, H phi, the classifier will function the same way irrespective of the domain. This is the idea. So now what we are doing is that we are using adversarial learning to ensure that we learn features in such a way that the features are domain agnostic. Once the features becomes domain agnostic, a classifier that has been trained only on the source features or any of the distribution can be used on the other distribution as well. So one might have this question, right? I mean, can we train this classifier separately, but not along the phi and the discriminator training? The answer turns out to be no, because the features have to be learned in such a way that it satisfies two objectives. One, they have to be domain agnostic. Two, they also have to be conducive for this particular classifier. Therefore, the classifier and the feature extractor have to be trained simultaneously, but one is trained using an adversarial objective, the other is trained using the usual supervised classification objective. But the feature extractor is trained using both the objectives of making the features domain agnostic and making them conducive for classification. Okay, this is one application of where adversarial learning can be used for a task other than generation.